for the review committee to accept this talk for the conference here. So this all started, and I like Milai's introduction here, with the Padme mission. And our goal was to determine whether or not we could send an ion mass spectrometer to Phobos and Deimos to determine the surface composition of those bodies. And so this work looks at the surface fluxes of ions coming off of Phobos and Deimos due to solar wind sputtering. So basically what we have is these impacts, such as the micrometeorites, asteroids, and the solar wind. They impact the surface of these bodies and they create an exosphere. We know that for lots of this stuff, it can be detected by a spacecraft, but I particularly want to focus on the smaller fraction of material that leaves the surface in the ionized state. That material can be detected by an ion mass spectrometer with very high sensitivity and low background, much better than you can get with a neutral mass spectrometer. So our goal is to correlate that secondary ion spectra to the surface composition and determine whether or not we can constrain the source or the origin of Phobos and Deimos, or maybe just Deimos, based on that detected composition of secondary ions. So to do this work, we used a couple of Monte Carlo programs. The first, SRIM, is a really popular program that has been used for a long time to calculate these sputtering yields. However, SRIM is, well, first it has a static surface composition, which means that every single ion that hits the target sees the same composition. However, processes such as preferential sputtering or preferential removal of weakly bound elements at the surface change the surface composition with time. And so we use this other program, SD-TRIM-SP, which updates the surface composition as a function of fluence. And this is basically what we see. So as we irradiate the sample to higher and higher fluences, we see that oxygen, which is the red line here, decreases with time, the silicon increases. And this is just SiO2, just a simple oxide for both hydrogen and helium bombardment at solar wind energies. And so as we irradiate along, we find that at high fluences, the surface composition eventually becomes approximately stoichiometric, meaning that for every incident or every ejected silicon, you get 2 ejected oxygens. And so another important constraint of these programs is that they're looking at amorphous targets, whereas in space you might have crystalline minerals as well as amorphous mixtures, and they don't take into account any chemical effects, which could be important as well. So the first thing that we wanted to do was to make sure that these programs are giving us accurate results for the total yield. Now the total yield is the combined yield of the ejected ions and the ejected neutrals. So what we find is SRIM, this program that's been used for years to do these measurements, overestimates the total sputtering yield at solar wind energies by a factor of 2 to 4, which means that past estimates have greatly overestimated the role of solar wind sputtering of these bodies. Now, SD-TRIM-SP, which is this newer program that updates the surface composition, matches the experimental data quite well. So these black dots here are the experimental data, and for these simple oxides, there's just not a lot of experimental data out there. A lot of it's older, but they seem to be doing a good job of matching this, especially at the solar wind energies. So we see here these black dots, I went ahead and assigned them a 20% uncertainty. Now, the papers that I got these from didn't actually include any uncertainties, and I think the experimental uncertainties could be a lot higher than this assumed 20%. So really, to do a better constraint of these computational models, we need more experiments measuring the total yields of these, at least for simple oxides. And so we've got the hydrogen on SiO2 and Al2O3. We also looked at helium. The matches for helium are a little bit worse than they are for hydrogen, but still at solar wind energies, which for helium is about 4,000 eV, 4 keV, It's within about 50% of these values, and for Al2O3, we're a lot closer to experiment. So SD trim SP seems to be giving us good total experimental yields. So we ran this program for more complex compositions, and here's just an example of the program run for a typical lunar soil composition. And we see that we get this depletion in lightly bound elements, again, the oxygen, magnesium, potassium, things with low surface binding energy are going to deplete from the surface, and we see an enrichment in other species such as the iron and titanium, the species with a higher surface binding energy. They become enriched on the surface. So it's important to note, though, that this program only gives us the total sputtering yields. It doesn't give us the ion yields, and in fact, the total sputtering yields are not directly related to the ion yields. But what we can do is use experimental measurements of secondary ion spectra to generate correction factors for these total sputtering yields. And so we've done this in the lab. We've taken several lunar soils. We've irradiated them with solar wind energy ions. And this is a typical secondary ion spectra that you see where I've normalized all of the ejecta to silicon at the 28 silicon here. And on the bottom, you have the secondary ion mass to charge ratio. And we see all of the major elements, aluminum, silicon, potassium, calcium, as well as a few molecular ions that sputter from the surface. And you can see here the silicon composition is actually the atomic percent of silicon at the surface is higher than aluminum, but you see more aluminum ions. Why is that? Well, here's an example of how we can generate these relative yields. Aluminum happens to have a lower ionization energy than does silicon. So that means that aluminum forms an ion more readily than silicon will. And for something like potassium, it forms an ion much more readily than silicon. And so even though we have a large or a very small composition of atomic percent of potassium at the surface, we can get larger ion yields because it more readily forms that ion due to the lower ionization energy. So these relative yields can then be used to correct a detected secondary ion spectra, and we refer everything here to silicon because silicon's present in most meteorites that we have in sufficient abundance to be detectable. So we can correct a detected secondary ion spectra in space to then determine what is the composition of an element with respect to silicon on the surface. So it's important to note here that there's, again, large experimental uncertainties, and I think if this type of experiment was done in a very systematic manner, looking at the effects of composition, of crystallinity, then we could reduce these errors and get a good idea of the corrective relative yields for these experiments. So we want to know composition, we want to know origin. So what we did is we ran these simulations for a large suite of meteorite compositions in SD-TRIM-SP, and then corrected those total yields using the correction factors that I showed on the last slide. And what we see is that our compositions tend to separate into evolved bodies such as the lunar, Mars, HED meteorite types, and the primitive bodies which are represented by chondrites, urolites, and aurites, which are down here. And there seems to be, for comparing calcium over silicon to magnesium over silicon, a really nice separation in the elements. And so we can also look at other elements such as iron versus aluminum, and again, we see there's a pretty good separation between the primitive and the evolved bodies. Although it's important to note that there are several little data points in here of some of these Mars compositions which really are outliers from the other groupings of the Mars. You can see down in here. And I'm not entirely sure what those compositions are. I'm not a meteorite guy, but On the whole, I think if we took a number of spectra or we had long integration times, we could get a really good idea of whether these bodies are primitive or evolved. So I just wanted to mention what is it that controls then the flux of ions coming off of the surface. And so one of the important things is the presence of oxygen in a sample has actually been shown to strongly increase the secondary ion yields. So if you have silicon metal, it's going to have a much lower secondary ion fraction of the total than will silicon dioxide, SiO2. For SiO2 stoichiometry, you get about 5% of the total silicon injected comes off as an ion. And one other interesting thing here, and again, another argument for the need of additional experiments, is this little data point over here. So this graph here is taken from Rick Elphick's paper in 1991. They looked at doing this type of experiment for, well, they did this experiment for a number of lunar analog samples and trying to motivate the use of secondary ion mass spectrometry to determine these compositions. And what they found was that looking at the total nuclear stopping cross-section, the noble gas ions sit on this really nice little line right here, but hydrogen gives you over an order of magnitude larger secondary ion yield than we expected based on only the nuclear stopping fraction. And we found this in our experiments as well. It's not published, but because it's rather unexplained right now, but hydrogen seems to give a much higher secondary ion yield than you would expect. And this could be really important for spacecraft measurements because you might be getting a lot more ions than you would expect based on these SC-TRIM-SP type programs. Okay, so in conclusion, we get a solid abundance of secondary ions coming off as a result of solar wind sputtering. For a typical solar wind flux that you would find at Mars radius, you get almost 10 to the third particles per centimeter squared per second, which is well within the sensitivity ranges of modern mass spectrometers or secondary ion mass spectrometers. You can use these secondary ion spectra to then infer the composition of the body, and that can then be used to constrain the body origin. We haven't looked at it in particular, but meteorite fluxes are also going to create ions, which could be detected and might be another source of maybe material from deeper in the regolith. The sputtered material comes from the top couple nanometers. Meteorite collisions might give you information of even deeper into the sample. And then there's a lot of uncertainties in these measurements still. We need more experiments. I'm about to graduate, so if anyone has a system that would allow me to do these measurements, I would love to talk to you. And that's it. Thanks.
Time for one question.
Hey, Micah, good talk. One quick question. Does SC-TRIM-SP also calculate vacancies and interstitials? And did you ever, if it did they also come to some kind of equilibrium in your surfaces?
So I haven't looked at what's happening underneath of the surface, but it's like TRIM in that it accounts for damage in the solid. So I don't know, but probably.
Interesting. Okay, cool.
Yeah.
Just one quickie. Have you looked at water ice yields? Have those changed since She et al. From many years ago?
No. So these programs don't do well with the ices because electronic effects. So you have nuclear stopping cross sections and you have electronic stopping cross sections. They're not. The electronic part is not handled well by these types of programs. But we have tons of experiments and those haven't changed at all.
Okay. Thank you.
Mm-hmm.
Okay, thank you. The last speaker.